VDMA and LONGi to present their latest PERC solutions based on M10 182 millimeter cells. That's what they are focusing on. And this will be followed by a panel discussion with executives from the 3 companies and TÜV Rheinland. So I'm now very happy to introduce our keynote speaker, Jutta Trube. Many of you know her. She's the director of PV equipment of one of Germany's largest sector associations, the German Engineering Association, VDMA. Jutta has a long background in solar and semiconductor, and Jutta will let us know what the latest ITRPV roadmap has to say on high efficiency solar. Jutta, welcome. The floor is yours.
Okay, thank you very much, Michael, for this invitation. So I think I will try to start my presentation. Is it now on the presentation? Can you see it?
Yeah.
Okay, fine.
Works.
So I was very pleased that I got the invitation to give the first talk today for this high efficiency solar conference. And I would like to show a little bit what's this year in the ITRPV roadmap, especially for the high efficient cells. And as you know, we are doing this every year with updates, and in autumn we typically look for the maturity, so how mature the technology is already for the production, and I will give you an insight on this now here. Okay. Okay. First of all, I'm with VDMA. So VDMA is the largest industry association in Europe. We have more than 3,300 members, and the photovoltaic equipment sector is one in this area. And we are dealing and they have members of all over the equipment sector from photovoltaics. As I said, we're running the ITRPV yearly with 2 updates. The next update is just starting, so I will give you the possibility also, if you have interest, to participate in our ITRPV. I present here a link, so you can go there, or you can go through the internet link of the ITRPV.org. So what is the ITRPV? We typically go through the complete value chain, starting with the silicon through crystallization, wafer, cell, module, up to the system. And this year we have had the 11th edition. Next year we will have the 12th edition. In 2020 we have had 57 contributors all over the world, and we increase every year the information content in our roadmap. So last year it was 19 figures overall, and this year it was 49 figures for all the areas. How does it work? We get from our participants the information on our questionnaire. We at VDMA are processing the data. So we are making average, mean, min-max values, but only the mean values we are publishing later on in the roadmap. And then we have an international chairs community over all the areas, especially also with Asian chairs. And with these chairs together, we decide which kind of information we will publish then in the next ITRPV edition. Now I will show you a little bit what I will talk shortly about the ITRPV. First, the status and the learning curve, of course. This is always one of the important parts. Then I will go through some of the results of the crystallization, wafering, cell modules with a special focus on the high efficiency, and then maybe only 1 or 2 slides for systems. And finally, I will give an outlook and a summary later on. So starting with the learning curve, we see that at the end of last year, we have had about 130 gigawatts, say, installed PV in 2019. This year, we think because of COVID-19, we will have a slightly decrease, maybe about 110 gigawatts. And we also see that, say, the average costs per watt peak is decreasing, as you can see in the last 3 years. The learning curve is still very deep if we just have a look for the last years. But if we complete or if we input all the information from the beginning, we have, say, about 23% as a learning rate. This year we have had, as I said, due to COVID, a flat shipment, but especially due to the changes in the wafer size format changes, we also will have a very bright format diversity for the modules. And as I said, PERC is still the PV working horse, even if we will discuss also the, say, increasing efficiency in the next part. Starting with the wafers, we see still, say, the P-type material is the biggest material and will stay the mainstream. But the casted material will decrease drastically. More the microcrystalline, but also the monocast material. This still will be present for some time, but the mono is the clear winner in the market. And especially the mono N-type market, this will gain fastly market share because of all the new technologies like heterojunction and IBC and so on. The problems with the LID that could be improved for the P-type with going to the gallium in the doping compared to the boron. And you can see that the gallium doping will increase in the market share drastically in the next years. So one big point is always how thick the wafer is, because this is a price factor in the production itself. Typically in past years, always thinner wafers were forecasted, but it remains at high values. But now we see that for the P-type and the N-type, the thickness is decreasing. And it's even more decreasing for the N-type material with a heterojunction. They are today already, so in 2020, already with 150 microns, and they think they can go down even 120 microns. But if you see in these red colors on the maturity, say all the thicknesses, say beyond, say, or lower than 130 micrometers are still in the red scale. That means that this is not really production proven yet. And with the P-type, they have the forecast only down to the 150 micron, but this could be fast organized, as you can see in the yellow color in the diagram. The sawing is nowadays nearly all diamond wire. There is nearly no other technology going on in the market. So what happens, especially in the last year, last 2 years? Say in the beginning, there has been only 5-inch wafers. Then they go for 6-inch, so the 156 in square, which was the dominant value. And it increases in 2016 slightly to the long-word standard, like 156.75. But in 2018, slightly bigger sizes, around 160 millimeter square came. So the M4 with 161 and the G1, which is like a working horse at the moment, the 158.75. But last year, say, a lot of different sizes came, but say crystalline is that maybe the M6, the M10 and the M12, so with 166, 182 and 210 are the formats for the next time. But this means that the module formats will diversify completely. We have also asked which of these sizes will become really in the market, and that's what I just said. It's the 166, and this will be used for the new and upgrades of the fabs, and the On the M10 and M12, so the 182 and 210, this will become only the format for the new fabs and tools from this year and next year on. But if we see that we have such a big amount of different kind of sizes, we think standardization, it needs to be come to really get prices down even in the equipment sector. So for the cell market, I show here the overview. You see the big working horse again is the PERCs, so the different technologies of PERC. The aluminum back surface field will disappear lately after 2024. And the new technologies like heterojunction, IBC and tandem will come on in the market in the next years. So the PERC is with a more than 65% market share in 2019, the mainstream, and will keep the mainstream from NP as well as in the N type, also with the passivated contacts types. And the heterojunction will reach in 2030 about 15%. Back contact cells are slightly less in the world market share, but even they will reach about 5% around 2030. But silicon tandem cells is what is, as we just heard, very active in research and pilot production. But say the communities see that this will come into production earliest around 2024. The bifacial cells and market will gain market share. We have at the moment about 20% bifacial ready, and in 2030 we will have about 80% with bifacial cells and modules. And PERCs and TOPCon of course are bifacial ready, so these are the cell types which should go in this direction. So coming to the high efficient cells, this diagram shows that the mainstream with PERC with aluminum oxide and silicon as a stack is still the mainstream. But the passivated contacts will gain market share, as you see in this light orange color. So this will come up in the next years and maybe will establish beside the other technologies what we may discuss later on as well. So what technologies would be used for this rear passivation? And you clearly can see here that the PECVD for the rear side deposition is at the moment the mainstream. It's with aluminum oxide and silicon nitride, but the ALD aluminum oxide will gain the market share. And we see that the passivated contacts have the trend that they will prefer the in situ deposition. So like tunnel oxide forming as well as polysilicon doping will go with in situ processes. Where does the process, the emitter doping goes in the near future? We see here the clear trend for the P-type material with passivated emitters. There are two different technologies: the homogeneous, which is with phosphor doping, and the selective emitter, which is then going with the additional laser doped technology. We see that the resistivity goes from 115 ohms square to 150 ohms square in 2030, and for the selective emitter from 140 to even 200 ohms square. And if we go for the N-type material with boron doping, you see that's still the main working horse here is the boron bromide for the doping material even for the next years. Another big deal is, cost factor is the materialization for the cells. And here we show the remaining silver per cell, and we see here it's dropping as forecasted as well. But here we have a look to the different kind of technologies. For the typical PERC material, we use about at the moment 90 milligrams silver for P-type cells. But if we have a look to the N-type, like the heterojunction, they need much more silver. And the color codes in the diagram show that, say, the heterojunction even will have work hard to reach about 110 milligrams of silver per cell in the G1 format. So, this is still some work to do. Then the bus bars, this is going clearly to the, say, high bus bar amount. So at the moment, we call it here 6++, but it's mainly 9 and even 12 bus bars is becoming the trend in the next years. So the 3 and 4 bus bars more or less are disappeared already. And if we have a look for the aluminum for cell, we see that if we go for bifacial use, even the aluminum could be reduced by 25%, or used only 25% of the material compared to the monofacial. So all this kind of topics will reduce the cost and go for the high efficient cell techs. So where will we end up with the cell efficiencies in the mass production? And here we have had a look to all the technologies, starting, say, even with the aluminum back surface field, so the gray ones, but then with all the perks for microcrystalline, mono P-perk and mono N-perk with passivated contacts. And if we compare this with the heterojunction, then we see that the N-type monoperks with passivated contacts are very close this year as well as in 10 years to the heterojunction technology. We forecast that in 10 years it's only maybe about 0.5% in the efficiency, and this may be a bridge to the silicon heterojunction. But what you can see also in the diagram, these are the blue triangles. These are the IBC technologies. These are still the head runner, and this can be combined maybe with all the kind of technologies which we have so far. But also the tandem cells we implemented here and ask for the expected cell efficiency if they come to the mass production, and see this will be clearly the top runner. But if we have a look to the readiness of the different cell technologies in the module factoring, then you see that the silicon-based tandem cells will maybe implemented after 2024, but the passivated contacts in N-type mono are already in mass production, like this yellow and gray line shows. And in the P-type, maybe there will be next year or so be implemented also in mass production. Now coming to the module, because as you know, we are now going with half cells, quarters, third cells, and maybe quarter cells. We have a look to the cell to module ratio, and we see that between mono and multi, it's about 1 to 1.5% difference for microcrystalline and monosilicon. And in the case of full and half cell, the CTM could get a boost of about 2% for half cells. And this means what does this mean then to the efficiency of the modules? At the moment, there is a lot of technology going on the modules. They change the difference or the distance between the cells itself. They have shingle cells and. So we think the best to characterize the different module types is really the watt per square meter and not just the watt per module, because we need to have a decent number to really compare. And there we see, if we compare, say, in this year, the P-type perk, we have about 202 watts per square meter. The N-type TOPCon have about 20.8, and the heterojunction have 210. And in 10 years, it will be slightly higher, so it goes again about 8. So this distance will become a little bit more, but this is similar like this year's. And we see that, of course, the N-type may be the highest efficiency for the modules at all. But for this high efficiency, as you can see here, we still need a lot of work to do to get this really in mass production. So what is the module power now for, say, the standard cell formats with 60 or 72 cells? We ask this for the full cells, but also for the half cells. And I have here just the comparison for the half cell information. And we see that, say, the P-type PERC in this year have about 345 watts, and will have in 4 years 355. And if we go for the bigger modules like the 144 half cells, we have the 415 to the 425 in 4 years, and the similar values for the others. But what does it mean? We don't have these cells and these module sizes really in the market anymore. We have had a lot of other module sizes coming on the market and in the mass production. So we see that already this, or maybe from next year on, say, modules which have areas of 2.5 to 3 square meter, and maybe even in 3 to 4 years up to 4 square meter sizes as module. So we have, we will have in the future a lot of different new cell types with together with the old, and to have yes, the higher powers on the modules will really appear, but with the increasing size on the modules. So what comes out on the product later on, we see here that the first year's degradation of the cells will be, say, at the moment is allowed a little bit more than 2%, but this will become more a standard like 2%, which they will guarantee in the next years. The product performance warranty is at the moment 25 years, will increase maybe to 30 years, and the product warranty will go up from 12 to 15 years. So what is what are the factors for this improvement? And we see the improvements in the cell, of course, overcome the LID by the gallium doping, the introduction of the 9 and 12 bus bars, but also the automatic optical inspection technologies. And in the modules, there are PD resistant encapsulations in place, and the half cell technology, and also the EMES systems. So all this will help to get the better products in the future. So what's with the systems? The most of the systems, as you know, go for power plants. This is the reason also for the increasing module sizes and the higher efficiencies. And also the reason for, say, that the system voltage is more and more going to the 1500 volts instead of the 1000 volts. And of course, also the tracking with the one axis may increase slightly in the next years, from about 30% to maybe 40, a little bit more, 40% in a few years. Now, the last outlook, how the photovoltaic market will increase. We have here a comparison of 3 different scenarios. One is just for a very small and tiny market. It's about the BNF forecast with a 22% global electricity market for photovoltaic. Then the electricity market for 69%. And the broad electrification market which includes also heat and transport in this. And you can see that in 2050, we will either end up with nearly, 8 terawatt peak, up to about more than 60 terawatt peak in installation in global. And that means the biggest addition per year, what we have to do with PV, is then ranging from 400 gigawatt peak in 2050 for the lowest assumption, up to 4,500 gigawatt peak in 2050. So I think we are on a good way, and we have several 100 gigawatt market ahead of us, and we can do this with, say, all the improvements what we have in the pipeline for the next years. And let's go on and do this effort to require really this X terawatt peak market. And ITRPV will help to guide you through this technology. Thank you for your interest. I would like to thank my contributors and chairs for the ITRPV. You can freely download the roadmap and the presentation at our webpage at itrpv.org. You can direct contact me, or if you really would like to contribute, you can see the link directly here and can fill out the Excel questionnaire and send it back to us. Thank you very much. I'm now open for questions.
Okay, thanks, Jutta. I think that was a great presentation. So I think we're running a little bit late. Maybe one question from me actually first. So I'm also working also for Solar Power Europe, and we're doing also market outlooks in terms of demand. It's not simple, and there are often many different numbers out there. So in terms of market demand, it's easier to benchmark than for technology, because there are not so many others doing it. So first of all, how comfortable do you feel with the research you are putting out? So what's the probability? Because I think for market researchers, I don't know, if we talk about demand, then we always do a high scenario and a low scenario. So what you show there, how high is the probability, Jutta, that this will come as you and your contributors think?
So for the market values, the last slide, this is what we are.
No, the last slide is okay. No, I think it's more about technology. I think it's because I think there it's pretty unique. There's also not so many others to benchmark with. Because if you talk about market demand, you have many, but technology forecasts are not so frequent.
Well, as I said, I have nearly 60 contributors to this data, and we at VDMA, we at least have in minimum 7 answers. Otherwise, we never would make calculations out of the things of the data. And so I discussed with my chairs also their opinions on the results what we are getting out there. And if they are a little bit afraid that this may be not really found the right direction, then we don't publish this data. So we publish the data which we are pretty sure that we have enough data for this statistics, and where say the ITRPV chairs also agree that this could be the right direction.
Okay, I think that's great. So again, I think everyone should really support ITRPV. They are doing really a great job. It's an important navigation compass for the industry, and very helpful. Maybe I think there's so many different questions, so that I just wonder if we touch many of that later. But maybe one question is about, I think a simple one was about HJT. So why can, for example, HJT be thinner than other than like a PERC incumbent, for example? Could you?
Unfortunately, I don't know the reason exactly why, but I have seen that they have, in principle, they have a totally different process value chain, so have different processes. And I assume it's with maybe with temperatures and say the type of machines which are they're using for the the processes.
Okay, I think so. We can discuss such detailed questions, and rather also on the different days. I think, Jutta, I would actually then rather, since we kind of are already running late with the first presentation, say thank you once again, and we continue and we take all these questions with us to the coming presentations. Again, so who has any questions, please get in touch with Jutta.